Okay, so today we're going to continue with our discussion of Bayesian statistics. And we're going to discuss difference between Bayesian and what we call frequentist statistics. Frequentist. We have to define frequentist too a little bit more. And then we'll do an example problem. So from the videos that you all watched, those homework questions, and then from some of the examples we talked about, what's kind of one of the big things you have learned about what is Bayesian statistics, and how does it kind of a different way of thinking? And we can kind of think about the example and that video of you meet a shy person and you're like, oh, they must be a math major, an engineering major, or something like that.
I think the way I think about it is that it just helps you deal with something. Like, prevents you from making generalizations based on previous past experience.
So it's a way to kind of call out our assumptions or biases, maybe. And this kind of shy person example. Well, so we meet them on campus, and we think, oh, they must come from some, quote unquote, science or math, right? Because we have this stereotype or this bias that people who are shy or introverted are from those kind of majors, or typically go to those kinds of majors. You all are very dynamic people, and I know this is obviously not a rule by any stretch of the imagination. But what did we learn going through that example about how Bayesian statistics can confront that, or kind of maybe disprove that? Yeah. We're counting for prior knowledge or information. And in this case, there are more business majors than math majors. So if you meet a random person, even though the prevalence of shy people in business majors is much less than the math and sciences, the random shy person you meet on campus or introverted person is more likely to be a business major just because of that probability in general of meeting a person. So this is this idea of Bayes' theorem and Bayesian statistics. It's been around for a while. It's been around for probably 150 plus years, but it hasn't really taken hold until the last 10, 20 years or so. And the kind of major paradigm of we'll call modern statistics over the last century has been based on the following. It's been based on hypothesis testing. That uncertainty lies within our experimental design. And data collection. So we can design an experiment, we can control for variables. If we want to reduce uncertainty, then we need to collect more data. And it's thought that this kind of method, and this is what we're defining, this general concept is what's known as frequentist. That this whole approach removes bias. Or subjectivity from statistics is something in fact different. We did this experiment, we did a treatment. Is a treatment group different from the control group? Everyone who eats Skittles in the morning, are they happier during the day? We give a group Skittles, we give a group no Skittles, and we test their happiness levels, right? And this frequentist approach, which we'll actually learn at the end of the semester, the last unit, is basically it's just totally objective. Do you meet this threshold for statistical significance or not? And this was kind of like the modernist approach of objective, just the facts, ma'am, kind of thing. But we've had a resurgence of Bayesian statistics. In the last, like I said, decade or two, and it's this just kind of from a conceptual level, this is embraces uncertainty. And human error. And we can explicitly account for uncertainty. Meaning we can mathematically account for uncertainty in our tests and predictions. So we'll learn linear regression, which is just a basic frequentist approach. There's Bayesian linear regression. We'll learn a t-test. There's Bayesian t-test. And the idea is we use Bayes' formula to account for the uncertainty in our variables underneath. And we'll kind of learn more about how that applies more explicitly. We can also say we can constrain our sample space, or we can constrain uncertainty or sample space. That idea of the prior, or what are the potential outcomes, the likelihood functions, there's bounds of real values, right? Trying to think about the information that we're putting in when we talked about the example of the COVID tests. What is the prevalence of COVID in the community at a given time? That can inform, it's not just like we can use that information to inform your probability of getting a test. A frequentist approach would ignore that information. What's the probability that it's positive or not? And it's kind of, it disassociates you from the reality or from the situation that you're in, the context. This is of, and then finally we can incorporate historic knowledge or scientific literature, right? Experience and opinion. And all of these things can be quantified in our calculations of probability. Using Bayes' theorem. So you'll read a little bit more about Bayes in that chapter to kind of give you some background about how that plays out. To use it explicitly in more complicated problems where we think of our prior probabilities being not just a single value, but a distribution of values. So for example, what's the prior probability, the distribution of rainfall depths over a 24-hour period? That's not just a single value, it's now a probability distribution, which we'll talk about on Friday. That's where things get more complicated. And the reason of the resurgence of Bayes' theorem is that we had more computational capabilities so it was kind of mathematically intractable to basically bring in one distribution and another distribution and plug that into Bayes' theorem. It's easy to do it with just probabilities and single values. So with R, and there's a lot of other tools out there that allow us to do the more complicated applications of Bayes' theorem. Okay, so let's do an example together. So this is a concrete test example. All right, so we're going to have concrete delivered to a construction site. Our past experience and testing. So just kind of, we know about this concrete that's coming from this particular vendor. Indicates that 80% of the deliveries meet our specifications. Has anyone taken in concrete or know about concrete? So specifications would be like compressive strength after so many days of curing or something like that, right? There's a couple important specifications. Each batch is a little different, right? They throw in some lime, they throw in some aggregate, sands. There's probably some other ingredients, right? And things could be a little bit off. So we not all deliveries are going to meet our specifications. So we need to test that, and we can test one sample. And usually that's you pour it, maybe you cut a cylinder out of it or you pour it into a cylinder and you let it cure. For so many days, and then you test its compressive strength. When I worked at the Bureau of Reclamation, they had a massive concrete testing facility where they would take cores that were like many feet in diameter out of a dam. Don't worry, they didn't drill all the way through. They would ship that out to the testing facility in Denver and do this huge compaction test. They had this one machine that was 3 stories tall that could compact these massive cylinders. And it would until they failed. And when they failed, there was an explosion that you could hear blocks away. It's pretty wild. Yeah. I think up to 3 feet in diameter. Yeah, it's pretty wild. The bigger you get, obviously, the more you can integrate around. and understand. Okay, so this test also has its own reliability, just like any test would, right? The test reliability is 90%. Let's talk about what that means. So 90%. So what this means is that quote unquote poor quality doesn't meet our specifications, concrete passes 10% of the time. Just like a COVID test isn't 100% reliable, I think PCR is probably really high reliability, but a rapid test is not. And so we'll define G as good quality concrete. And we'll define T as passing the test. The sample passes the test, right? So good quality concrete is just, is it good or not? The test, then when we test it to find out if it's good, right? But that's not necessarily 100%, but it's not. Okay, so what's the probability that we have good quality concrete from this plant, given the problem that we set up? %. So from that plant, 80% is good quality, so 0.8. And then the probability of passing the test, given that it's good quality, is equal to Jaden, what do you think?
Is it 90%?
90%, exactly. So this is the reliability. And then we can also say the complement of that. And Jaden, do you mind trying to do that? What is the complement of this conditional probability?
Is it the 10%?
Right. How would I write that out with this symbology?
It would like be P parentheses T given G, like with a complement over it, or like the line over it.
Exactly.
Yeah.
So we pass the test given that it's poor quality, and that's 10%. Great. All right, so let's do some stuff with this. We've kind of written out what we know so far. And here's our kind of our first question. So say a cylinder passes a test. What is the actual probability that it is good quality? Or we'll just say that it meets our specifications. Okay, so Sam, why don't you take a crack at just the symbology of this sentence? How would I write this sentence out? What is the probability that it meets our specifications given
Quality of that is the one that denotes that it meets our specs, right?
So G means it's good quality, it meets our specs, exactly. Yeah, T means it passed the test. Okay. And you'll notice that that's the opposite of this, right? Okay. So what we're going to do now is write out Bayes' theorem for this. And just to do that, the kind of rhythm or the algorithm is, so probability of G given T is equal to the probability of T given G times the probability of G divided by all the options. So we take this and we repeat it again, T given G times the probability of G plus, what's the other option here? Probability of T given not G times the probability of not G, or complement G, right? So these are basically the two options. And this gives us the kind of total probability theorem for the probability of T. Okay. So we could say, whoa, the probability of getting good concrete is 80%. Well, we have some information, and that allows us to kind of refine that. So let's actually calculate this. We got a good test. What's the probability that we have good concrete? Do you think it's going to be higher or lower than 80%? I hope it's higher because we actually did a test, right? So that gives us more information. Therefore, we should get a better number. So let's plug these numbers in. T given G, that's the reliability of the test. That was 0.9. Probability of G is 0.8, 80%. You could kind of think of that back to the COVID example. That's like the general population of what's happening in COVID in the community. And then we get all these things down here. So 0.9 times 0.8 plus 0.1 times 0.2. And all that equals 0.97. So we did that test. Now we have more information. It updates our ability to predict that the probability that sample is good and it meets our specification. So we went from 80% to 90.97%. We have updated our prediction. The concrete meets our specifications. Okay, so let's do one more round of this. And this is where the Bayesian updating algorithm comes into play. If we test a second cylinder, we can improve our prediction. Using what's known as Bayesian updating. So we say we test the second cylinder and it passes. Okay, so that's some new information. So we have two passing cylinders. And now our probability of G good given we tested becomes the prior. What was the probability of G? Because we've already tested it. Now we know we have a 97% chance that it's good. And we can use that to update that. So now we're going to test the probability of G given our second test, so test 2, is equal to the probability that we pass a test given that it's good times the probability that it's good given that we pass that first test, right? This is what we're updating right here. This is our prior. And then times, and then we have to just duplicate everything again. So probability that we test given that it's good times the probability that it's good given we did that first test. Okay, so that comes down here too. Plus the probability that we test given that it's not good times the probability that it's not good. So these are the two places where we update that probability. This is also updated. So what is the probability that it's not good now? That's 1 minus 0.97, essentially, right? So yeah, so 0.03. So this is updated too, because we know, given that test, that we have a much smaller probability that it's not good. So let's write this out, 0.9, that stays the same, times 0.97. All over 0.9 times 0.97 plus 0.1 times 0.03. Now that we can do all that, our probability that we have a good concrete, given that we did 2 tests, and we did that Bayesian updating, becomes 0.997, or almost 1%, right? So this is basically the probability that we have good concrete, given that we did test 1 and test 2.
So the first probability gives it. Start this process.
Yeah. Yeah, exactly. So we're kind of taking like, oh, past experience, that 80% number from the concrete lab. It's like, maybe that's just, something that you read, or that's something they gave you, or just your past experience. That's a rough number. You do a test, you can update your probability and refine it. And then of course you can keep testing, but is it worth, at some point you're getting diminishing returns. So at this point you could say, well, 97% versus, essentially 100% with that second test. Just like taking multiple tests for public health or whatever can refine your probability. I should update this with like a COVID rapid test and put the actual numbers in there, because I know everyone's been doing those. Any other thoughts or questions about that? The key thing is to remember, what are you updating? We know now that the probability that we have poor concrete has to be updated because we've done that test. That's new information. And the probability that we have good concrete has been updated because we already have that information from the previous step.